Hello guys, welcome back to ptet.chemistry channel. So my name is Mr. On, and in this tutorial video, I'll continue this topical playlist on topic 4, which is just on stats of matter as well as ideal gases. So this question is about a general gas equation, which is essentially the ideal gas equation. We started out with PV equal to nRT, where n is the number of mole. So I can express it in terms of mass over the molecular mass times RT. So this is going to be the mole of the gas if you know the mass of the gas, which is mass in m gram. So the mass is m gram and the mR is going to be gram per mole. So really just rearrange the equation, move the mR up there and the PV can move down there. This is your simple cross multiply. If you can't see it, then you can imagine it's time mR both sides. So this one, the mR will be disappearing and you have mR here, and then you can divide by PV both sides such that you will lose the PV on the left hand side, because PV times mR over PV equal to mR, and you will get mRT over PV. So some people who are a bit stronger in maths, you have been able to move both of these expressions down there and mR up there very easily. But some of you who can't see it, then you probably have to think of it using this mathematical expression because of the equal sign. So whatever you do on the left, you do on the right as well. That's the meaning of equal. Alright, so the correct expression there really is mRT over PV. So this is a very straightforward question. It seems to be a knowledge type of question, but really if I know my ideal gas equation as stated in the syllabus, I would be able to rearrange this just by relating number of mole to mass over mR for the gas. Question 37, so I have ethanol. Ethanol has a boiling point of 78 degrees Celsius. So at that pressure and at that temperature, this is at 79 degrees Celsius, so just above the boiling point. The ethanol vapor does not perfectly obey the gas equation. The key thing really is does not. So the ideal gas equation has assumption, and these are the things that stated in the syllabus that you should know the assumptions for when an ideal gas behave ideally. That is the most important one being negligible intermolecular forces. Of course, when you have CH3 CH2OH, you know that when you have hydrogen bonded to a highly electronegative element like oxygen, fluorine or nitrogen, we can draw the dipoles. It's very polar. I can draw the lone pair on the oxygen, and they form hydrogen bond with a neighboring molecule of ethanol. So they form hydrogen bond between their own molecule. So dipoles, lone pair, as well as label the hydrogen bond. So H bond is among the strongest intermolecular forces compared to permanent dipoles, compared to van der Waals generally. So as a result of hydrogen bond being a very strong, strongest intermolecular forces of attraction, so force attraction between different molecules, between the discrete molecules. So the ethanol vapor does not perfectly obey the ideal gas equation as a result of it. Alright, so the best answer would have been B, because that is to do with significantly strong hydrogen bond between the molecules. They don't specify it, but hydrogen bond is a form of intermolecular forces between the molecules. As usual, in theory paper, you could be asked, use a diagram to explain why this is true. So the diagram would involve you showing the hydrogen bond, showing two molecules at least, the dipoles, lone pair on the electronegative element, and then the labeling of the intermolecular force there. Question 38, so which of the following least resemble an ideal gas? Alright, so as mentioned, an ideal gas has assumptions. The most important assumption, as I mentioned in the previous question, is to do with negligible intermolecular force. So we're assuming it has close to none intermolecular force. If we want it to be ideal, we want it to be least ideal. So least ideal meaning most non-ideal. Most non-ideal mean break the assumption the most. Okay, so your most important assumption is to do with intermolecular forces being negligible. So when you break the assumption the most, you're looking at very significant intermolecular force, just like the previous question. We have ammonia, we have helium, we have hydrogen, we have methane. So in terms of van der Waals forces, all of them have van der Waals forces. However, between helium and hydrogen, both have 2 electrons, but H2 has bigger surface area simply because it has 2 atoms. So you have, surface area. So you have 2 atoms in one molecule of it, whereas this one only has 1 atom. So despite both of them having 2 electrons only, this one will have stronger van der Waals, because van der Waals depend on not just the total number of electrons, but also surface area. And you can look that up under structure and bonding, which you have covered in any textbook, as well as your notes, your lesson, maybe when you first did the lesson, really. Okay, so permanent dipole. So permanent dipole is to do with whether you have symmetrical distribution of charge in your molecule or not. NH3 definitely is polar. Helium is what you call non-polar. Hydrogen is non-polar because you have 2 atoms that have the same electron negativity. The same deal with CH4, which is a tetrahedral molecule. When you have a tetrahedral molecule, you have got 4 bond pair and 0 lone pair. The 4 bond pair repel equally, giving you tetrahedral geometry. The 4 atoms are the same in a tetrahedral arrangement, meaning to say the dipoles cancel out exactly. There is no overall dipole. So no overall dipole as a result of symmetrical distribution of charge due to the 4 atoms being equal, okay, in the tetrahedral geometry. Okay, so the other one, of course, if you don't have permanent dipole, you automatically has no hydrogen bond, because you have no permanent dipole to begin with. Hydrogen bond is a result of a very polar bond, which is to do with OH, NH, and FH. So here we have a hydrogen bonded to a nitrogen, so we do have hydrogen bond, and because they increase in strength generally, so hydrogen bond is the strongest intermolecular force generally compared to this and this. Therefore, we are looking at ammonia that will break the assumption the most by having the least negligible intermolecular force, because this is quite strong, so it is not negligible. Next question. So this is a calculation question. So we're looking for identity of the gas. They give you the equation very generously, but of course we are dealing with mass and also molecular mass. So I'll use this expression where this can be used to substitute the mole of the gas. Mole of gas is the mass of the gas divided by the MR of the gas. The identity of the gas can be obtained by knowing the MR. So this relates to one of the earlier question about the expression that you can get for the MR of a gas as determined by the ideal gas equation. The job really is, once you rearrange the equation, only then you think about the value to sub in. Alright, so the mass M is the mass of the gas. So when you have that fluorescent light tube that is not the gas, you fill it with a gas, and then the mass increased by 1.02. So that is the mass of the gas, alright, not the mass of the tube, because the mass of the tube increased by this much. So this is the mass of the gas. The molar gas constant is given in the data booklet, 8.31 joule per mole per Kelvin. These are given in the data booklet. Your temperature will be in Kelvin, which is already provided. Your pressure has to be in Pascal or Newton per meter square. This is kilopascal. Kilopascal is not Pascal, so it's 101 times 10 to the 3 Pascal. Or you can express it in Newton per meter square, because 1 Pascal equal to 1 Newton per meter square, but not 1 kilopascal. So we have to multiply by 1000. Okay, and then the volume. The volume is probably the hardest bit in this question. There's 300 cm cube. The volume in an ideal gas equation, as you could see, Pascal is equivalent to this SI unit of Newton per meter square. We have to get meter cube as our volume in our ideal gas equation. That's one of the key mistakes that a lot of students couldn't get. Alright, So start from 1 cm is equal to 10 to the power minus 2 meter, which is the same as 1 over 100 meter. Alright, so you know that 1 meter is 100 cm, so 1 cm is 1 over 100 meter, which is 10 to the minus 2 meter. This is exactly what is stated in your maths curriculum back in upper secondary, really. And then what you do is you cube both sides, so you get 1 cm cube is equal to 10 to the power minus 2 meter cube. This is also part of indices. 1 cube is 1, cm cube is cm cube, 10 to the minus 2 cube is 10 to the power minus 6, meter cube is meter cube. So what we get really is the volume is going to be, what was it just now? 300 cm cube. So that is 300 multiplied by 10 to the power minus 6. That's how we convert cm cube to meter cube very easily. I never memorize this thing because I am a bad memorizer. So what I do is I just remember the most basic thing, and I could get them because I know my maths, and most likely you'll be doing maths if you're doing chemistry. Most likely, alright, but these are not like A-level maths, these are probably like elementary maths. Okay, so having gotten all these value, then sub them in very carefully. As with any calculation, you gotta try and do them twice on your calculator to avoid making any mistakes with pressing in your calculator and stuff. So I've gotten my MR as 83.9. I'll just double check my calculation because you know I will have made mistakes here and there before, so I want to try and avoid making mistakes by not working too fast and not making careless mistakes. So I got that answer again, 3 significant figure. So have a look at your data booklet for your periodic table. So 83.9, so these are all noble gases, right? So look at the noble gases. 83.8, that's for krypton. Krypton is the closest, so B must be the answer there. Question 40 is another ideal gas equation calculation. So P equal to nRT, but we are trying to find molecular mass, and these are just expression. You don't even need to put calculate the value. You just need to get the correct expression. So they want the MR. So there is mass over MR. MR is going to be MRT over PV. So of course we are looking at M is equal to 0.15 gram. So that is the organic compound that is vaporized. So that is probably going from solid to gas or liquid to gas, does not matter. But mass does not change because you are just changing the states of matter. So conservation of mass is an important concept. So the mass of the gas is the same as mass of the solid or the liquid that you vaporize. Okay. R is going to be 8.31 joule per mole per Kelvin. This is the molar gas constant available from your data booklet for free. Your temperature is at 405 Kelvin. Your pressure is at this Newton per meter square, which is equivalent to Pascal. Newton per meter square is the SI unit already, so there's no need to change anything at all. But your volume is in cm cube, so for the same trick that I had in the previous question, I really just need to think about 1 cm is 10 to the power minus 2 meter. Cube both sides, so I can just cube both sides. I'm working a lot faster here because I already shown you one time in the previous question. So now my volume is just 65.0. cm cube convert to meter cube, I'm sorry. This time 10 to the power minus 6 meter cube. So I don't need to calculate anything here. So I just need to make sure that I have the correct value. 0.15 times 8.31 times 8.31. So there is no 8.31 here, so this is wrong. There is no 8.31 here, so A is also wrong. The 8.31 is on top there, multiplied by 405, so the top bit is the same. The bottom bit, 1.00 times 10 to the 5 is the same. This is times 10 to the minus 6 because of the conversion factor, cm cube to meter cube. So I'm looking for 10 to the minus 6 and not 10 to the minus 3, which is wrong. So D is the obvious answer there. Alright, so that's it for this 5-question series. And if you enjoy my tutorials, so don't forget to click the button on the bottom right, subscribe to the channel, and please share the channel widely with all your friends, your chat group, your study groups, your juniors, your seniors from school, your relative, and many other people. Don't forget that the channel has O-level and IGCSE topical playlists as well, so they'll be suitable for any 14 to 16 years old who are studying chemistry, whatever curriculum they are doing. And these 16 to 18 years old A-level, topical playlists will have been suitable for any 16 to 18 years old, A-level, or even IB chemistry learners, standard level or higher level, wherever they are in the world. Okay, so thank you for watching, and I'll see you in the next tutorial video.